Hey everyone, welcome to this explainer. Whether you're deep in the plastics industry, working in Masterbatch, compounding, or injection molding, or maybe you're a student just stepping into the fascinating world of color matching, you are exactly in the right place. Today, we are breaking down the absolute heart of every professional color laboratory, the spectrophotometer. We're finally moving away from those endless, frustrating arguments over whether a particular shade is navy or midnight. Because let's face it, while the human eye can perceive millions of colors, getting two people to actually agree on just one of them is nearly impossible. Instead, we're going to dive straight into the pure, objective science of perfect color. Here is our quick roadmap for today. First, we'll cover why matching by eye simply fails. Second, we'll officially meet the spectrophotometer. Third, we'll unpack the science behind LabStar and Delta E. Fourth, we'll walk through a real industry workflow. And fifth, we'll wrap up with common errors and best practices. All right, let's kick things off with Section 1, Why Eye Matching Fails. It's time to talk about a massive, relatable pain point in the manufacturing industry. Picture this. A customer walks in, hands you a physical sample, and says, "I need the exact same blue." What's the operator's next move? Do they just kind of squint at it and start mixing pigments by sight? Well, in modern industries like automotive, medical plastics, or FMCG packaging, doing that is practically impossible. Every single person's eyes are different. Someone's mood, their age, or honestly, even what they ate for breakfast can subtly affect how they perceive color. Plus, a color looks completely different in the warm morning sunlight compared to sitting under a harsh LED bulb in a warehouse. Simply eyeballing it is a recipe for disaster. Just think about the financial stakes here. If a global brand runs a massive production order of shampoo bottles and the blue packaging doesn't perfectly match when stacked side by side on a supermarket shelf, they will reject the entire shipment. Literally millions of dollars lost, all because someone trusted their eyes. So the crucial point here is that the human eye is entirely subjective. It's inherently dependent on lighting, the individual person, and the surrounding environment. The spectrophotometer, on the other hand, it is completely objective, highly repeatable, and purely scientific. It takes that highly subjective human experience of blue and converts it into a standardized global number. This is exactly why global supply chains rely entirely on machines, not human perception, to generate their critical quality control reports and approve shipments. Moving right along to Section 2, Meet the Spectrophotometer. Let's introduce the scientific solution to our deeply flawed human perception. Okay, let's dive into this because there's a beautifully simple concept we really need to understand right up front. The machine doesn't actually see color. The machine analyzes light. That right there instantly de-jargonizes what's happening under the hood. The instrument isn't looking at blue or red the way our brains do. Instead, it's analyzing exactly how much red, green, blue, or yellow light is actively reflecting off an object and precisely which specific wavelengths are being absorbed by the material. So, to give it a formal definition, a spectrophotometer is a scientific instrument that measures light reflected from a surface and converts it into precise numerical values. In short, it gives color a true scientific identity. Instead of just calling a piece of molded plastic blue or sky blue, the machine assigns it a highly specific set of mathematical coordinates. These numbers form a unique signature that'll remain exactly the same in any laboratory, on any machine, anywhere in the world. Let's walk through the highly logical, step-by-step process happening inside the hardware when you press that measure button. Step 1, a precisely calibrated standard light source, usually a xenon flash or an LED, fires and hits the sample. Step 2, the physical chemistry of the sample immediately absorbs certain wavelengths of that light and reflects others. Step 3, the instrument's highly sensitive internal detector receives that reflected light. Step 4, the onboard software instantly generates a detailed spectral graph of every single wavelength. And finally, Step 5, that complex graph is seamlessly converted into actionable numerical values, specifically LabStar and Delta E. All of this happens in just a matter of seconds, but the level of precision is absolutely staggering. Now, if you walk into almost any professional lab, you're going to see specific brands dominating the workbench. X-Rite, for instance, is a massive industry standard across plastics, automotive, paint, and packaging. And why is that? It comes down to exactly what we just discussed, incredibly high accuracy and high repeatability. When you combine that robust hardware with excellent software and lightning-fast measurements, you create a trusted global standard. This universal language means a buyer sitting in an office in Germany can completely trust the exact same color data produced by a manufacturer operating a plant in India. All right, Section 3, the science of LabStar and Delta E. Let's make these complex metrics incredibly simple to grasp. And this brilliantly illustrates the LAB system, the mathematical grid that gives every single color in existence its unique numerical fingerprint. Think of it like a giant 3D coordinate system. L stands for lightness, running on a vertical axis from 0 for pure pitch black, all the way up to 100 for pure brilliant white. The A value operates on a green to red axis, where negative numbers mean you're pushing into the green, and positive numbers mean you're pulling into the red. Lastly, the B value operates on a blue to yellow axis. Negative values pull toward blue, and positive values push toward yellow. With just these 3 simple coordinates, you can perfectly plot any color the human eye can see, and millions it absolutely can't. But knowing those coordinates is really only half the battle in a production environment. When a customer sends you their physical standard, and your lab creates a new production sample to match it, you need to know the exact mathematical difference between those two items. That difference is known as delta E. It is the absolute most important parameter a quality control engineer will ever use. It mathematically defines, without any emotion or debate, if your match is a pass or a fail. Now, what's really interesting here is the breakdown of these incredibly strict industry tolerances. A delta E of absolutely 0 is a perfect match, though practically speaking, that's like finding a unicorn in manufacturing. A 0.3 is considered an excellent match. A 1.0 is generally acceptable for a lot of commercial consumer goods. But once you hit a delta E of 2 or 3, the human eye can suddenly and easily see the difference between the two parts, and the customer will almost certainly reject the entire batch. And if you're working in the automotive industry, man, their tolerances are notoriously unforgiving, often requiring final delta E values well below 1.0 just to even be considered for approval. So let's move into Section 4, Real Industry Workflow. It's time to apply these metrics to a real-world day-in-the-life scenario. Here is the exact journey of a high-stakes customer order. Minute 1. The QC engineer receives a physical blue automotive clip as the standard. The clock starts now. Minute 5. They carefully clean the sample to remove any microscopic dust and rapidly calibrate the machine. Hour 1. They measure the standard, get the exact LabStar coordinates, and R&D instantly starts formulating, mixing raw pigments, and extruding granules to make a physical injection-molded sample. Hour 2. They pull their new plastic sample from the mold and measure it against the standard. If that delta E comes back too high, they immediately adjust the formulation, add the required pigments, and repeat the entire loop until that incredibly strict tolerance is achieved. Science dictates every single step of this high-pressure workflow. Let's ground this data in reality for a second by looking at a white Masterbatch order. The standard L value, the lightness, was supposed to be 97.50, but the production sample came out of the machine at 96.90. Now, that might sound like a tiny, totally insignificant drop in the L value, but to the machine, it means the white has become noticeably dull. Why did this happen? Well, it could be a slightly low dose of titanium dioxide, or maybe just poor heat dispersion in the mixing phase. But because the spectrophotometer caught this objective drop in lightness early, the engineer can fix the formulation right on the factory floor before shipping it out. That completely saves the company from facing a massive, incredibly costly batch rejection from a very angry buyer. Let's move to Section 5 and see how this builds into some highly actionable advice, errors, and best practices. First and foremost, daily calibration is absolutely compulsory. It is completely non-negotiable. You must calibrate your machine using the white tile and the black trap every single day before you take a single measurement. If you skip this critical step, the internal baseline of the machine slowly drifts. This happens because of subtle temperature changes in the room, ambient humidity, or even just the natural aging of the internal light bulb. If that baseline drifts, it will start giving you incorrect values, and you'll end up chasing your tail, formulating the wrong colors over and over again, and potentially ruining entire massive production runs simply because the machine wasn't tuned. Finally, I want to give you a rapid-fire, high-value checklist of common measurement errors you absolutely have to avoid. Dirty samples, scratches, dust, or even a simple oily fingerprint on the plastic will scatter the light flash and give you a wildly false reading. Selecting the wrong illuminant in the software, like measuring for daylight when the customer explicitly asked for store lighting, will completely skew your data and guarantee rejection. Or trying to measure highly curved or transparent samples without using the proper opaque backing procedures, that's just going to give you useless numbers. Controlling these physical variables is the absolute secret to achieving first-time right color matching. It drastically reduces trial costs and minimizes customer complaints. So we've covered the hardware, the numbers, the high-speed workflows, and the costly pitfalls. The global demand for these technical skills in the export, packaging, and automotive industries is quite literally higher than it has ever been. So I leave you with this. Knowing what you know now about the inherent flaws of human perception and seeing the staggering precision of this technology, are you still trusting your eyes, or are you ready to trust the science of Delta E? Thank you so much for joining this explainer, and we will see you next time as we continue to decode the fascinating world of color science.